This was the slide that we ended up on for Chapter 9, limitations of the localized electron model. And it has several limitations, not the least of which is it does not handle multiple Lewis dot structures very well. In other words, you can have things like nitrate. Like that. You would have to resonate that with two other structures. In order to use the Lewis dot format. Right? And that's not reality. I mean, that's just a temporary fix. Sometimes we would, let's use this one in the middle. Sometimes we would say that, make these partial bonds, right? But that wasn't even a good fix, because when you do that, there's no way to assess the electrons, because how partial is partial. Right? So we needed a better theory. Along with these other problems. No, don't do that. I thought I had it fixed. Turn that off. Temporarily. I was still doing it even with the speaker. All right. Well, fooled me. We'll turn that back on. Oh. Well, made a liar out of me. That's the message I got this morning. See how long it lasts. Okay, the other things that the valence bond theory couldn't do was it doesn't handle free radicals. If you have a molecule with an unpaired electron, you don't know what to do with them. I mean, you just have to assume that it's one of those groups when you do the VSEPR and try to figure its geometry. And it doesn't provide a way to calculate bond energies. Just doesn't. All right, so we're going to go on to the molecular orbital model. All right, this is where our understanding of bonding stands now. And it's gone through several iterations. It's developed over the years to accommodate larger and larger, more complex systems. We're going to stick with really easy ones, like the homonuclear diatomics, like dinitrogen, dioxygen. We may dip our toes into the heteronuclear diatomics like NO, just for argument's sake. But the core of the molecular orbital model assumes no longer that those bonding electrons, in fact, none of the electrons of the atoms belong to individual atoms. They belong to the collective. It's kind of a communist philosophy. Right? The molecule itself owns all the electrons, and those electrons are distributed however it wants over its entire structure. That's the primary difference between the valence bond theory and the molecular orbital model. So what we have to do is create another orbital structure for the molecule that parallels somewhat the atomic structure that we drew for electron electron structure for atoms like oxygen. If oxygen has 8, we would draw the structure like this, like that. Yeah. And there's a parallel structure that we would draw, say, for if we had a diatomic, say oxygen, we would have a similar looking structure, only there are some significant differences. And we're going to get into those in just a minute. So this is a side-by-side comparison. The localized electron model, of course, relies on atomic orbitals and their overlap to form bonds. Whereas the molecular orbital model, let's see, for my own benefit, I'm going to shrink that, put it out of the way. Molecular orbital relies on a new model of orbital structures. And that's enough said right now. We'll get into more details later. In order to use the localized electron model with quantum mechanics, you had to do some major mathematical tweaks to expand quantum mechanics into the molecular realm. The quantum mechanical solutions are different in that their solutions are not tweaks and extensions from the atomic quantum mechanics, but they're an entire new set of mathematical expressions that work for molecular orbitals. So while the electrons in the localized electron model are assumed to be localized to an atom or between two atoms, if they're localized to an atom, of course, they're lone pairs or core electrons. If they're in the bond, then they have to be shared between atoms. But for the molecular orbital model, all the electrons are assumed to be delocalized over the entire molecule. And that's kind of an odd way to think about it until we hit our next few slides, and that I hope that will become clear how you do that. By the way, the more delocalized you can make your electrons, the more stable. If you try to pack an electron into a small package of space, it becomes less stable. So if you can spread them out, delocalize electron density, then you can stabilize the structure. This still holds true for both of the models, 2 electrons per orbital. So whatever we call an orbital in the molecular orbital model still only contains 2 electrons. And the energies are still quantized. That is, whatever this wave function says for atomic electron probabilities is not transferred wholesale, but the idea that the energy is quantized. In other words, when an electron moves from one molecular orbital to another, there's no in between. It's all or nothing. That's what that means. Come on. There we go. There was a delay. Back up. There we go. Okay, so in order to generate molecular orbitals, we take the atomic orbitals and combine them. We generate new molecular orbitals. So in the process, as the bond forms, any atomic orbitals that belong to the individual atoms disappear in favor of molecular orbitals. And the number of orbitals is conserved. So if you have 4 orbitals involved between the 2 atoms, and when you get the molecular orbitals constructed, you have 2 plus 2 is 4. You have 4. So we conserve the number of orbitals in the molecular orbital model that pre-existed in the separate atoms. And the way we do that, since if you combine several orbitals from either atom, say we're only dealing with 2 atoms, just for simplicity, then we have what we call bonding and anti-bonding orbitals. And I know that's like I'm just wah right now. That doesn't make any sense. But I've got a video that should help with the concept. When we talk about interference, then it should become a little clearer. So if in these molecular orbitals, the probability of finding an electron is centered on the axis between them, we still call this a sigma bond, a sigma molecular orbital, just like we did with the valence model. And then if the two atomic orbitals give some sort of a construction where they're off axis, those are pi molecular orbitals. And this last statement, I think I've covered that already. The atomic orbitals are obliterated in favor of the molecular orbitals.
Waves can overlap. When that happens, the highs and the lows can build upon each other. Or they can align in such a way that they balance each other out. When they build upon each other, this is called constructive interference. When they balance each other out, this is called destructive interference. Let's look at what happens step by step when two waves travel through each other. Here's a moment when two highs overlap. This results in a combined high that's much higher. This is constructive interference. Now, here's a moment where all the highs are perfectly overlapping all the lows. We see a cancellation of the wave amplitudes. This is a moment of destructive interference. If you took a snapshot photo, you might think that nothing is happening. Change that to a video, and you'd see otherwise. In the next moment, you've got a case where the two lows are now overlapping. This results in a combined low that's much lower. Once again, we have constructive interference. So, constructive and destructive interference never occur at the same time. Instead, they alternate, one after the other. And then the two waves continue on their merry way, having traveled right through each other, amazingly unaltered. Check this out. A wave can bounce off of a rigid structure. Let's add a second wave. Cool. Let's add a second wall and try to confine a single wave. Aha. What we've got here is called a standing wave. Notice that to have a standing wave, the dimensions have to be just right, typically some multiple of the wave's wavelength. A musical instrument, such as a guitar or a flute, is engineered just right to accommodate standing waves, vibrating within the instrument, producing beautiful sounds. That's good energy.
Okay. So there was a discussion about interference. And in order to make that work for our molecular model, we have to think of electrons as waves. Remember in the earlier discussion, difference between the particle versus wave nature of light, and then we can extend that to matter also. So we normally consider light as energy or as waves, but it also has a particle nature, and that was proven through the photoelectric effect. But the flip side of that is that particles or solid matter has a wave nature also. And when you get down this small, the size of the electron, then the wave nature is a significant factor. And it turns out that understanding electrons as waves helps build this molecular orbital model. In fact, it was responsible for building the earlier models also in quantum mechanics, treating everything as waves. Okay, so here's some other terms. We encountered interference here, so it can be constructive or destructive interference. And for those those wave examples that were given on the video, the wavelengths and the amplitudes actually of those two waves were exactly identical. So that when you got to destructive interference, you got a flat line because the highs and lows were exactly equal and spaced exactly the same wavelength. But you can have complications where you have waves of different wavelengths and different amplitudes interacting. And this is called superposition when you have two overlapping waves. Their interferences, constructive and destructive, still occur, but they're not complete, like our example. And in fact, that concept of interference is behind the use of what we call multiplexing, where you have a signal that's sent from here to there, and it can be different types. It can be AM radio, FM radio, it could be fiber optics. And you superpose another signal on top of it. So you have constructive and destructive interference, but that wave now that you send down the line can be decoded at the other end. Right? For, say, an FM station, they send it out over the waves, and your radio is set up so that it will destructively interfere with the carrier wave. And what's left behind is the signal. So you can hear the music or hear talking or whatever at the other end. All right. Like I said, you can get very complex patterns. And that's the rub, as they say. Trying to get your quantum mechanical mathematical expressions to properly predict the nature of these interferences within the molecule. So here's an artist's rendition. If we have a hydrogen atom that has a, let's say we have one hydrogen atom here. Let's see, I need a new marker. If we have one hydrogen atom here with this electron, right, and we have another one over here with this electron, then we know that this one starts out with an atomic orbital 1s1. Right? That's all there is. And I think they're calling this one A and the other one B, just to keep them apart. Well, if we're going to have molecular orbitals from these two atomic orbitals, we need two molecular orbitals. So when we combine them, this, let's draw it on an energy scale. Say energy is this one. All right, so we have this 1s here, and we have 1s here. Right? Leave electrons off for now. We're going to build two more molecular orbitals. The bonding molecular orbital is lower energy than either of these two. So it's down here somewhere. And then the anti-bonding is up here. So now we started with two and we end with two. And since the bond is on axis between the two, this is a sigma. That's going to be a sigma molecular orbital in the bonded pair. Right, so for this one, we have O2. That's where we are here. This is what the atomic on this side. Okay, so lots of times we draw dotted lines to show where the origins of these two. Right, so this is a sigma, and it's derived from the 1s orbitals of either side. This is a sigma with a star. And we use the star to designate anti-bonding, just to keep them separated. And this is also derived from the 1s orbitals. Okay? That's where we're headed. This artist's depiction shows you that the bonding orbitals have their most probable location for the electron are between the nuclei of the two. So I'm going to be in here somewhere, in between. And the anti-bonding has a node right in the middle. In other words, the anti-bonding puts the most probable out here. And this is based upon the quantum mechanical math that was developed for molecular orbitals. These calculations give you that appearance. So obviously, if the electrons are between here, then you're forming a bond. And if electrons are out here, you're forming an anti-bond. So anti-bond bad, bond good. Okay. But you need both of them because you started off with two, you have to end with two. All right, I said that before. This molecular orbital is going to be lower energy than the two that started with, and the anti-bonding is going to be higher energy. Okay, I used a slightly different terminology, but this is more common than the one they're using. I think it's easier to follow. And we use we fill the orbitals with electrons from low to high. So we've got two electrons here that come from either side, one from here and one from here. And we go into lowest orbital first and move our way up. All right, so this one would have to reverse its spin or it has to start at a different spin anyway. But both of them go into a bonding orbital. And that's good because we've decreased our energy, and decreased energy means stable. There's another way to that we're going to cover in just a minute to determine whether the scenario that you built for molecular orbitals is acceptable or even probable. We'll go to that. We'll get there in just a minute. Now, the thing about the molecular orbital model is that it has built into it ability to calculate bond energies. So the bond energies that are calculated using the molecular orbital math agree with actual measured values. So that's an advantage to the molecular orbital model. It calculates energies that agree with the experimentally determined values. Let me see. Okay, that second item just references the way we, the notation that we use for molecular orbitals. These are going to be sigmas because they're on the axis. They're either in between the atoms or they diametrically opposed for the anti-bonding. And we try to use a similar notation to show us the origin of the orbitals. Like that, sigma 1s. Shows you that it's a sigma bond and it's derived from the 1s orbitals from either of the two contributing atoms. And we can write electronic configurations for, so if we were to write just like we would write one for oxygen for O2, then its electronic configuration would simply be sigma 1s with 2 electrons in it. That's it. Very simple. All right. We said that before, the number of orbitals are conserved, and of course the electrons are conserved. That's a no-brainer. You can't create or destroy electrons in the process. You got to account for all of them. So F2, difluorine, has 18 electrons. So this would be an example of its electronic structure. And in this case, let me do it from here. Here we go. In this case, we're including the the core electrons too. The point there is that when you build a molecule, everybody's in the game. I mean, nobody's sitting on the bench. Right? All the core electrons, all their orbitals contribute. Everybody goes into the game. Now, for simplicity's sake, we usually leave out, when we draw these types of diagrams, we usually leave out the cores. So if we went to something higher like difluorine, we would generally leave out the sigma 1s and the sigma star, because they're going to be the same no matter what, and you get variability in the valence orbitals. So the molecular orbitals derive from valence orbitals. All right, so don't get confused. If you don't see a 1s down here for one of the drawings, it's because that's convention. We just leave them out. But in this diagram here, you do have the 1s's included, just for completeness. Okay. All right. So I mentioned a way to calculate whether or not a stable bond is predictable. And the way we do it is we calculate bond order. So bond order is calculated by taking the number of bonding electrons, in this case 2, and subtracting the number of anti-bonding electrons, in this case 0, and divide by 2. And we get a bond order of 1, which runs parallel to the concept of a single bond. When we draw it the other way, wait a minute, that's not oxygen. You guys just let me go right on down the road with oxygen. That's hydrogen. We can do it for oxygen, but not with that diagram. I need a different diagram. Okay, so back up and substitute hydrogen everywhere I said everything else. So when we calculate, I can put it up here. There we go. We would expect a single bond. If we drew the Lewis dot structure, it would be like this. That's it, just a single bond. So there's not a direct one-to-one relationship, but we can infer a single bond from this. The difference is that bond order doesn't have to be a whole number. It can be fractional. Whereas single, double, triple, they're all whole numbers, and then we have no other choice. But if we have a positive value here, that means that it's possible to form that molecule as written. All right, so there we go. That diagram looks more like the one I drew here. Yeah, that one looks more like that one. Okay, suppose, what if we add an electron to this mix? Say if we do like this. Just add an electron. Right? You can do that experimentally. Where would it go? This one's already full. So we have to move up here, don't we? And put one there. Now, I don't know where it came from. It could have come from either side. It doesn't matter. Now that we're in the molecular orbitals, 2 go here, 1 goes there. So what does that do to our calculation? Now we've got an anti-bond. And our bond order is 1/2. We went from a 1 to a 1/2 bond order, which destabilizes. It may be possible to form that molecule, but it's not as stable as an H2 neutral. Okay. What else we got? Oh, hold on a second. This one's going to run for a while, but can't be helped.
Today we're going to discuss molecular orbitals. But before we can get to molecular orbitals, we have to first consider atomic orbitals, something that hopefully we're all pretty familiar with. So let's start with hydrogen. Here I have two isolated hydrogen atoms. And we know that each isolated hydrogen atom should have one electron located in the 1s subshell when in its ground state. And of course we know that these electrons don't move in perfect circles around the nucleus as I've depicted them here, but they do define a region of space defined by a sphere. But when two atomic orbitals combine to help form a chemical bond, something special happens. In the case of hydrogens, those two 1s subshells combine and form a region of space known as a sigma molecular orbital. And a sigma molecular orbital is a region of space where the electrons live generally in between the two hydrogen nuclei, screening the repulsive force that their positive charges have on one another. So they stabilize, keeping these two nuclei close together. This is a bonding molecular orbital. But there's one rule that we haven't yet considered, and that is that the number of atomic orbitals going into an MO system must be equal to the number of molecular orbitals that that MO system contains. So our molecular orbital system is not yet complete in this depiction. We have one more molecular orbital that forms. That new molecular orbital that forms is called a sigma star molecular orbital. And it looks quite different from the sigma MO, doesn't it? If there were electrons inside of this sigma star molecular orbital, they would spend most of their time outside of the two nuclei, not screening their positive charge repulsions, and therefore would actually make the system very, very unstable. So let's think about what that means in terms of how hydrogen atoms come together to form a bond. In order to fully understand the molecular orbitals of an H2 molecule, we have to plot them in terms of energy. So here in this depiction, I've shown the two atomic orbitals here as these lines in blue. That will be our non-bonding energy. Unless there's an energetic benefit to forming molecular orbitals, these two atoms aren't going to get together and do that. So bonding molecular orbitals will be lower in energy, and antibonding orbitals will be higher in energy than this purple line that I've drawn. So let's combine these two different atomic orbitals into molecular orbitals and see what happens. When this happens, we always get a combination that is sort of centric around that non-bonding energy. In this case, we formed two new molecular orbitals from our two atomic orbitals. One is the sigma, one is the sigma star. Next, we have to populate our new molecular orbital system with the electrons that we know the atoms are bringing to the party. In this case, one from each. When we do this, notice that those electrons go into a lower energy orbital overall, and this lowers the overall energy of the entire system. So this energetic benefit that comes from forming and populating molecular orbitals leads us to the prediction that hydrogen will form a bond to another hydrogen. But beyond that, we can actually calculate exactly how many bonds will form. We call this the bond order, and it's calculated quite simply, using the number of bonding electrons minus the number of antibonding electrons, divided of course by 2, because we know it takes 2 electrons to form a chemical bond. In our example here of hydrogen, we have 2 bonding electrons, and we have no antibonding electrons. Consequently, our equation tells us that we expect 2 hydrogen atoms to get together and form a chemical bond with an order of 1. In other words, a hydrogen molecule should have a single bond. And that is, in fact, exactly what we see. Now let's move on to the next element on the periodic table, helium. Now I've put molecular orbitals here in quotations because, as we're about to discover, there really is no such thing as a helium-2 molecule. But to prove it, we need to use our energy diagram and combine the 2 atomic orbitals of helium atoms to find out what the energetics of bonding would be if it were to happen. So let's go ahead and do that now. We combine them into a system with a sigma and sigma star molecular orbital, and then we populate that system. Now, in this case, I have 2 electrons that can fill the sigma bonding molecular orbital, lowering the overall energy. But I still have 2 more electrons that have to go into this new molecular orbital system. And they have no choice but to go up in energy and populate the sigma star. The consequence of this is that there's no real energetic benefit to bonding, so 2 helium atoms have no real incentive to get together and form an He2 molecule. And in fact, that's exactly what we see. When we calculate the bond order, we find that 2 bonding electrons and 2 antibonding electrons leads to a situation where we predict a bond order of 0. In other words, we don't predict a bond at all. And when we study helium in the laboratory, that's exactly what we find. Helium exists as isolated atoms. Now let's expand our discussion and consider the molecular orbitals of elements from the second row of the periodic table. We're going to begin with fluorine. Now, fluorine, we know, has available p orbitals because it's in the second row of the periodic table. So atoms of fluorine have 3 different 2p orbitals to donate to forming new chemical bonds. And within those orbitals, we know each has 5 electrons. So let's think about, first, how those atomic orbitals combine, and second, how those electrons can populate the new system energetically to make something that's beneficial. When we combine p orbitals, we find that we have a system that looks a bit different, don't we? In this case, a grand total of 6 atomic orbitals must combine to form a grand total of 6 molecular orbitals. Now, the lowest and highest in energy of these correspond to the in-phase and out-of-phase overlap directly along the nuclear axis. Those we would call the sigma and sigma star molecular orbitals. But we have some new players here. Those are the orbitals that result from the side-to-side overlap of p orbitals that we call pi and pi star MOs. So we have to figure out exactly where the electrons will go in this system and whether or not there's a real energetic benefit to putting them there, and that will help us determine whether or not fluorine will make a bond. Let's do that now. When we put all of our bonding electrons in, we notice that 6 total electrons go into bonding molecular orbitals. This is a tremendous energetic benefit. The sigma and the pi bonding MOs are completely filled. But fluorine has extra electrons, and they have to go somewhere. And the next best available option is to place them into the pi star molecular orbitals. These are antibonding, so the energy comes back up somewhat. However, notice that overall, we still have a system in which, on average, our electrons are in lower energy locations when they're in the molecular orbital system. There's a little bit of an energetic benefit here. And our calculation for bond order lets us know that when you have a grand total of 6 bonding electrons and a total of 4 antibonding electrons, you would expect that species to form a single bond. And in fact, when we study fluorine in the laboratory, that's exactly what we find. A molecule with a single bond. Now let's move on to something a little bit more complicated. Here's another second row element, nitrogen. Nitrogen also has 2 p atomic orbitals available, but in this case only 3 electrons in each. So let's combine those and form a new molecular orbital system. You might notice something changed here, right? Notice that the sigma molecular orbital is actually higher in energy than the pi. And this is an interesting phenomenon. It's caused by something called sigma pi mixing. And we won't go into great detail into it here, but I wanted to point it out because this is how you'll probably see it in your textbooks. Nonetheless, when we use the electrons from nitrogen's 2p orbitals to populate this new MO system, notice that they all go into bonding MOs. And better than that, there's nothing left. There are no extra electrons to fill in those antibonding MOs and counterbalance the energetic benefits. So this is a tremendously energetically beneficial arrangement. When we calculate the bond order of an N2 molecule, we find that having 6 bonding electrons and absolutely no antibonding electrons, we expect a nitrogen molecule to have a triple bond. This is a very strong bond, which makes nitrogen gas almost completely inert. And again, when we go into the lab and study nitrogen, that's exactly what we see. A diatomic molecule with a triple bond. Now let's consider one more element from the second row of the periodic table. This time we'll consider oxygen. And I promise, I'm not wasting your time here. We're going to see something new. Now, just like any other second row element, oxygens have available 2p subshells. And we know from their electron configurations that each oxygen contains 4 electrons in those 2p subshells. So let's combine them to form some molecular orbitals. When we do this, we don't see any real surprises here. Sigma, sigma star, pi, and pi star molecular orbitals form. 6 atomic orbitals in, 6 molecular orbitals out. And if we fill them from the lowest energy to the highest, we notice that 6 of these electrons will go into bonding molecular orbitals, giving us a nice energetic benefit. But there are still 2 remaining electrons. And here's our new question. They clearly should go to the pi star MO, but should both electrons go into one, or should they each take a separate molecular orbital for themselves? The answer to the question is rooted in Hund's rule and the Pauli exclusion principle. Electrons will try to spread out and maximize spin. So, when they populate this new molecular orbital, they do so like this, raising the overall energy a little bit, right? Not enough to completely counteract all of those bonding electrons, so there will be a bond formed here. O2 molecules do exist. But even more importantly than that possibly is this. Notice that there are unpaired electrons in this molecule. And that means that our new oxygen molecule is paramagnetic. Liquid oxygen can be trapped within the confines of a powerful magnet. You may have seen this demonstration done before. And of course, just as before, our prediction is correct. If we calculate the total bond order of oxygen using 6 bonding electrons and 2 antibonding electrons, we find that the 6 and the 2 leads us to a calculated bond order of 2. Oxygen exists as a diatomic molecule with a double bond. So I hope that by now you're beginning to appreciate the power of molecular orbital theory. It not only confirms so many of the other topics we've already discussed on bonding, but it allows us to explain completely new properties that all of our other theories couldn't, things like the paramagnetism of oxygen. This is just the beginning of molecular orbital theory. You may want to consider in the future things like molecules that consist of 2 atoms that are not the same, or molecules that consist of even more than 2 atoms. There's much, much more to explore. But for this lecture, we're done. Thanks for watching, everyone.
And finish their advertising. Since I'm using this for educational purposes.
Today we're going to discuss molecular.
Oops. There we go. Okay, so there were some new topics introduced there, but I hope the overall discussion was more coherent than the one I was giving you, or at least it's in a different voice. So the molecules we've been looking at so far are homonuclear. That is, the same element combine 2 atoms each. Those are the simplest and easiest to draw diagrams for. And notice that in the latter 2, they didn't even use all the valence electrons, right? These atoms in this row, they have valence electrons in the 2s orbitals that could combine, and you can draw those in, but it won't have any impact on the bond order calculation. He was focusing on the business end, so to speak. So I mentioned this idea of paramagnetism and diamagnetism. Versus diamagnetism. And it's an observable phenomenon. they mentioned oxygen was paramagnetic and gave you the reason why. But what you see is when you have one of these big, I got a slide following this one on it. When you see liquid oxygen poured into the gap between the big, one of these monster horseshoe magnets. It's about that far apart, but they're huge. The oxygen will sit right in there in between as long as there's space, and then of course excess will flow out. But that paramagnetism, that is attraction into a magnetic field, is due to unpaired electrons. If you have paired electrons, then their spins cancel each other out. And they don't have anything to respond to a magnetic field. But if you have one or more unpaired electrons, you will get this attraction into the magnetic field. So this is attraction into the magnetic field, and this is repulsion. Oops, I learned to spell. So we tried that with, let's see, nitrogen, right? He showed us nitrogen where it's 6 minus 0 divided by 2 is 3, triple bond. So there are no anti-bonding electrons, and all of the bonding electrons are paired. Then this would be, an example would be oxygen, and this one would be nitrogen. It would be repelled by the magnetic field because all of its magnetic moments are paired up and cancel out. And that's what we observe. We can measure the magnitude of each of these phenomena with a special device. I've got a little diagram in here. One of these slides coming up. Oh, there it is. So you have this balance, and this is a diagrammatic. I mean, this is not necessarily the way the device is built. Maybe the original one was. You have an analytical balance which is very sensitive, and you lower your sample into this magnetic field, and you measure as you approach it whether or not it's pulled into the field or it's repelled by the field. And that you can gauge the magnitude of the paramagnetism or the diamagnetism. And previously, the valence bond theory had no way of predicting or explaining this phenomenon. It's only with a molecular orbital theory that we can now have a way to explain why this one is diamagnetic and this one's paramagnetic. And there's our big horseshoe magnet. On the left, they're pouring liquid oxygen into the gap, and then on the right, you see some of it remains in that gap. If you have a pacemaker, I wouldn't get too close to one of those. Oh, Professor Dave. I wonder how long he's going to talk. 9 minutes. Okay. Well, let's give him his voice.
It's Professor Dave. Let's revisit molecular orbital theory.
He knows a lot about the science stuff. Professor Dave explains.
We've learned a bit about molecular orbital theory and the ways in which it differs from valence bond theory. But let's expand on this knowledge now so that we can understand a phenomenon called sp mixing. But before we get into that, let's take some time to review the basics. First, let's compare valence bond theory and molecular orbital theory. Valence bond theory considers covalent bonds as being localized between a pair of atoms, resulting from the overlap of atomic orbitals or hybrid atomic orbitals. This overlap results in sigma or pi bonds, and we can use this theory to predict molecular shape. However, there are simple molecules that do not conform to this theory, like the diatomic oxygen molecule. Given this Lewis structure, where each oxygen atom has a full octet, we would expect oxygen to be diamagnetic and weakly repel a magnetic field. However, it does in fact exhibit paramagnetism, as liquid oxygen is attracted to a magnetic field. To explain this, we have to turn to molecular orbital theory, which differs from valence bond theory in that electrons are considered delocalized throughout the molecule, and atomic orbitals combine to form molecular orbitals, which are also delocalized throughout the molecule. These can be sigma and pi bonding orbitals, or sigma star and pi star anti-bonding orbitals. This theory ends up being better equipped to predict the arrangement of electrons in a molecule in certain situations. This is due to a process called the linear combination of atomic orbitals. In the modern physics course, we talked a little bit about the wave function, and molecular orbitals are combinations of atomic orbital wave functions. Just the way the wave function describes the behavior of an electron within an atom, molecular orbitals describe the behavior of an electron within a molecule. And just like atomic orbitals, they are filled when they contain two electrons of opposite spin. This theory requires that we strongly consider the wave nature of the electron. In the classical physics series, we talked a lot about waves and interference patterns. So to get the full picture of wave behavior in order to better understand molecular orbitals, check out this tutorial now. Otherwise, we simply need to understand that when two atomic orbital wave functions are combined, like these two s orbitals, there can be constructive interference, where the peaks line up with the other peaks. This causes the amplitude to increase, which results in a bonding molecular orbital, like the sigma s orbital. Most of the electron density is between the nuclei, which strengthens the bond. There can also be destructive interference, where the peaks line up with troughs. This causes the amplitude to drop to zero, resulting in an anti-bonding orbital, like this sigma s star orbital. Here, there is a node between the nuclei, which weakens the bond. The bonding orbital is of lower energy and will thus be filled before the anti-bonding orbital. For this to make more sense, we simply need to understand that these images of waves are just two-dimensional analogies to help us visualize the type of overlap. Electrons are three-dimensional objects, so the waves are in 3 dimensions, and constructive interference thus results in regions of greater electron density, while destructive interference results in regions of no electron density, which are depicted by these bonding and anti-bonding orbitals. We can do the same thing with p orbitals, utilizing direct overlap, which will yield sigma px and sigma px star molecular orbitals, or lateral overlap, yielding pi and pi star molecular orbitals from the overlap of py and pz atomic orbitals. Orbital number is always conserved, which is why the linear combination of two atomic orbitals will always result in two molecular orbitals, one bonding and the other anti-bonding. We can depict these linear combinations with molecular orbital diagrams, as we have seen. The dashed lines show how the atomic orbitals on the sides combine to form the molecular orbitals in the middle, such as we see here for hydrogen, with two 1s orbitals combining to form one sigma s orbital and one sigma s star orbital. If we go up to the electrons in the n equals 2 shell, we can see the 2s orbitals combining in precisely the same way, and then the 2p orbitals combining as follows, with the sigma bonding orbital and then pi bonding orbitals, followed by the corresponding anti-bonding orbitals. The good news is that these orbitals are still filled according to the Aufbau principle and Hund's rule, like we already know. This means that we fill them from lower energy to higher, according to Aufbau, and we will put one electron in each orbital for a set of degenerate orbitals before doubling them up, according to Hund. We've already learned in a previous tutorial how to fill in these MO diagrams for certain diatomic molecules, like O2, and how to use them to calculate bond order. Here's that diagram one more time, along with the calculation for bond order, with 10 bonding electrons, including the sigma 1s bonding electrons, and 6 antibonding electrons, including the sigma-1s star antibonding electrons. 10 minus 6 is 4, and 4 over 2 is 2. This explains the double bond in diatomic oxygen. But we also get an explanation for the paramagnetism of the oxygen molecule. We have 2 unpaired electrons in these antibonding orbitals, which does predict paramagnetism for this molecule. This is an example of the success of molecular orbital theory, as no other theory can account for this behavior. Now that we are up to speed, let's go over one other thing. The molecular orbitals that result from the combination of the 2p orbitals exhibit this order in O2, but this will change for other homonuclear diatomic molecules. Let's look at this diagram, which depicts the relevant orbital energies for all the potential homonuclear diatomic molecules in the second period, from lithium to neon. As we go to the right in the period, effective nuclear charge increases, so the atomic radii contract, and the orbitals get lower in energy. On the left, the pi 2p bonding orbitals are lower in energy than the sigma 2p bonding orbital, but on the right, the sigma 2p bonding orbital dips below and thus will be filled first. This discrepancy is due to a phenomenon called sp mixing, which influences the energies of these molecular orbitals. This happens when the sigma s and sigma p wave functions combine in such a way that the sigma s orbital becomes more stable and the sigma p orbital becomes less stable. As a result, we see the sigma s and sigma s star orbitals going lower in energy and the sigma p and sigma p star going up in energy. So much so that the sigma p orbital now sits above the pi p orbitals. Molecules like O2 and F2 have negligible sp mixing because the 2p orbitals in those atoms have some paired electrons. This raises the energy of the 2p orbitals, making them too dissimilar to the energy of the 2s orbital to allow mixing to occur. But going to the left on the period, where p orbitals have unpaired electrons or are vacant, the 2p and 2s orbitals are of similar enough energies that sp mixing will be prevalent and the order of the molecular orbitals will switch. While this is an interesting phenomenon, if we are only using these diagrams to calculate bond order, it won't matter because it is just the order of bonding orbitals that is being rearranged, so it won't affect a bond order calculation. Nevertheless, we have hopefully reached a more sophisticated understanding of molecular orbitals. Thanks for watching, guys. Subscribe to my channel for more tutorials. Support me on Patreon so I can keep making content. And as always, feel free to email me, ProfessorDaveExplains@gmail.com.
One of Professor Dave's middle videos. He started off with long hair and looked like a real reprobate. And then he started cleaning up, and now a lot of his videos are nicer clothes, and he's trimmed, and he's spouting his leftist nonsense. But these are scientific videos, and he can't throw his politics into these too easily. So I still use them. Okay, the phenomenon of sp mixing has to do with the way that the atomic orbitals come together and form the molecular orbitals. As a practical matter, trying to figure out which one is which, you just go to the periodic table, and anything to the left in these two periods, second, third, anything to the left will have sp mixing, and these to the right will have no mixing. Which means that for no mixing, you're going to have the sigma and the pi, and then the pi star and the sigma star. That's the way oxygen and fluorine would be. And then to the left for nitrogen, these would switch. like that. So this is no mixing, and this is mixing. Sometimes it's referred to as sigma pi mixing, and that's probably more accurate, but SP mixing is kind of stuck. Okay. Here's another way of approaching it with some more information. This diagram also gives you magnetism for the different homonuclear diatomic molecules. So diboron is going to be paramagnetic because you see these unpaired electrons. There's carbon. Carbon's going to be diamagnetic. Nitrogen will be diamagnetic. Oxygen we've seen is paramagnetic, and difluorine is diamagnetic. And it all has to do with whether or not they have unpaired electrons. And down here we've got some gives us some idea of the bond energies, right? Single bond, let's see, that's a triple bond. This is double bond, this is single bond. And then of course, the bond length, the stronger the bond, the shorter the length. Just draws the atoms closer together. That's an animation for SP mixing versus no XP mixing. Okay, and your review documents have these diagrams in the back, so you don't have to memorize it. All right, how about heteronuclear molecules? How do we deal with those? Well, it becomes more and more difficult for people like us who are not steeped in quantum mechanical mathematics to get a handle. I'm not a chemistry major, and I don't think any of you are headed for chemistry majors. So what we want is just to have a way to handle it. In other words, an explanation that is reasonable, not necessarily mathematically rigorous. So in this case, we have carbon and oxygen in a molecule of carbon monoxide. And the atomic orbitals for carbon are at a higher energy level than oxygen. And this is principally due to the fact that, get down here. No. This is principally due to the fact that oxygen has more protons. So it draws the orbitals, the atomic orbitals in. And carbon has fewer protons. Its atomic orbitals are higher up in energy. So that's why they're drawn the way they are, with higher energies for carbon, lower energies for oxygen. But when you put them together, you get this 2s here from the 2s, and generally speaking, the s's mixed with s's and p's mixed with p's. But I've seen some diagrams where the mathematics tell you that sometimes p's and s's mix to give you the molecular orbitals. But in this case, we get this 2s from carbon and this 2s from oxygen. Is that showing? It's kind of small, isn't it? Gives you the sigma s here and the sigma s star here. And then when you combine the p orbitals, we get the sigma here and the pi above it, rather than the pi underneath. So we've seen some mixing here, right? We should see, if there's no mixing, then the sigma and pi should come first, and then the sigma and sigma star should come after that. So the mixing is a little, I guess, for lack of a better term, wonky. Anyway, once you've got the molecular orbital diagram, then you can fill the electrons in and calculate the bond order. And in this case, the bond order should be 3, right? We've got 2, 4, 6, 8, minus 2 is 6, divided by 2 is 3. So carbon monoxide should have a triple bond. And that's what we predicted with the valence bond theory. We had it set up like that. That would be carbon monoxide. So this is got an octet, that's got an octet. But that doesn't tell us whether or not this molecule is diamagnetic or paramagnetic. In fact, it is diamagnetic because all the electrons are paired. Let's see. Oops, went too far. Okay, what if we have hydrogen and fluorine? In this case, we're forced to mix an S. Let's see. Preambles here. The 2p orbital of fluorine is at a lower energy than the 1s orbital of hydrogen. And that's principally due to the fact that fluorine has 9 protons and hydrogen only has 1. So its first orbital is going to be way out here. And the p orbital, besides the fact that it has so many more protons, p orbital is out here anyway because it's got to make room for the 1s and the 2s, and then the 2p can come along. Okay, so we've left out the one from the fluorine. We've left out the 1s and the 2s simply because they're already used. And hydrogen only has a 1s. Fluorine has a 2p that's available. And when we mix them together, we get a sigma and a sigma star with these energies. And like I said before, these are mathematically calculated. And the sigma star is higher than the 1s, and the sigma is lower than the 2p. So we find that when these 2 electrons go into that orbital, we get a bond order of 1, which is what we would expect HF to be, single bond. Yeah, I already said that. Okay. We may also be able to infer something having to do with electronegativity. We would expect based on what we've learned so far about electronegativity, that fluorine is very high electronegative, hydrogen is middle of the road. So the electron density should move toward fluorine. And if we go back here and look at where the sigma bond has formed, right? It's closer in energy to the fluorine atom than it is to the hydrogen atom. So that implies that the distribution of electron density is going to be closer to the fluorine. I think that's what it's trying to illustrate there. Okay. And that's what this slide just says. And that runs parallel with the predicted bond polarity that we've assigned to the HF bond in the past. Now, the concept of delocalization. This is particularly applicable to molecules that require, in our previous valence bond theory, require resonance, where you have the 2 or 3 or 4 different structures that have to resonate. Delocalization is useful for these. And in this case, we're actually going to combine the localized electron model and the molecular orbital models to get some sense. So usually when we get unused p orbitals, like we determined with our previous hybridization scheme, those p orbitals, if they have electrons in them, can overlap and give us double and triple bonds. But if they're arranged correctly, they can form a continuous delocalized electron density over the entire molecule. And it takes special conditions, but it tends to stabilize the molecule. And if we think of it in those terms, that gives us a better understanding of the actual molecule as opposed to resonance, which simply says those 2 or 3 different Lewis structures have to go flip-flopping around. Here's a good example, benzene. Benzene is an organic molecule. It is extremely stable. If we had to draw, well, I'm not going to draw it. There it is right there. If we drew the Lewis structure, it would be, well, maybe a little explanation would be in order here. In organic chemistry, when we draw something like that, wherever 2 lines meet, that's a carbon. We just don't write the carbons in because it gets messy. Okay. And in this case, we have 1 hydrogen attached to each one. Now we do write the hydrogens. Carbons are the only ones that we don't write. So if we want to specify an atom other than carbon, you have to write it in. Okay. Now notice that only gives us 2, 4, 6. There's no octet for that carbon. So that's why the double bonds. Okay. So now this one has an octet, that one's got 1, that one's got 1. They all have 1. But this can also resonate with a structure that has the double bonds here, here, and here. Just, I mean, that's a valid Lewis dot structure. That's the way we would have to draw resonance for benzene. But the experimental evidence tells us we would expect this bond to be shorter than that one. Right? Because the single bond is lower energy and farther apart, and this would be shorter. But experimental evidence says all these bonds here are exactly the same length and exactly the same strength. Right? So we know that that's not an accurate representation of the bonding in benzene. We would tend to, with the valence bond theory and the localized electron model, we would tend to overlap hybridized orbitals, right? 1, 2, 3. And that, if you have 3 and you need a hybrid orbital, it's sp2, correct? Okay. So that only uses 2 p's. That means we've got an extra p up here and an extra p down there, and these overlap to give you the double bond, right? According to our previous theories. And it would look something like that right here with these p orbitals, and they overlap. Well, if the bonds are equivalent, then we can't just overlap between here and between here and between here. What we have to do is delocalize this pi system over the entire molecule, and that's what this shows. And so those pi orbitals delocalize, and that adds stability to the molecule. We call this conjugation. If it's a linear molecule where you have alternating, see, I'm going to draw 1, 2, 3, 4, 5, 6. So let's see this hexane. But if we form a double bond there and a double bond there, then the conjugation of the system occurs if you have a single and a double alternating like this. So you can form a delocalized system over these, between these carbon atoms. And that stabilizes the molecule also. But that's conjugation. If you, under certain circumstances, when you get these ring structures where all the carbon atoms, in this case, are in the same plane, you can get unstressed overlap of those p orbitals and form this ring structure. Then you get an aromatic system. Whereas this is simply conjugated double bonds. This is aromatic. And the stability of the system goes, the energy goes down, and the stability goes way up for aromatics because of that complete ring structure. I studied pigments in crawfish processing waste. We used to catch the crawfish and sell them to companies that would process them, get the tail meat out and package it, freeze it, and send it all over the world. Well, the crawfish is only 15% tail meat. So you got 85% waste. What do you do with it? That was part of my job and part of my professor's work was try to figure out what to do with that waste. Well, if you've ever seen a lobster or a crawfish or a crab that's been cooked, especially, they're bright red. That pigment in there has this structure to it. It's a really long chain, but it's conjugated. And the more conjugation you got, the lower the absorption energy. So you can lower it so far that it goes into the red. So that's just an example. You see the same thing in beta carotene in carrots, like orange vegetables. And some others. So I won't waste your time on that because we're past time. So this is what the nitrate would look like I drew it earlier. If we assigned formal charges to each of the atoms, that's the way that would look. The double bonded oxygen would be a 0 formal charge. The other two oxygens would be negative, and nitrogen would be positive, and you'd have to resonate them. I drew this alternate structure where you're representing partial bonding. That still doesn't matter. This is really what it looks like. You get this delocalized pi electron network over the molecule, and that stabilizes it further. Not further, that stabilizes it as measured. Okay, one last slide. So a theory tries to explain why things happen and tries to, whenever possible, quantify something that's measurable. And with the molecular orbital theory, we're able to calculate bond energies. With this technology, this technique, this photoelectron spectroscopy, we can actually measure the molecular orbital energy levels. And that's what we're showing here with this diagram. These are molecular orbitals. See, they're identified over here, right? And these are the transitions that the electrons would have to, they'd have to absorb this amount of energy to go from here to infinity, right? 0 energy. They ionize, they leave the molecule. Okay, so how do we get at it? Well, you have photons, high energy photons of a specific energy that you can very finely control. They could be X-rays for all I know. And so you calculate, you know the energy that's going in with your photons. And then you measure the energy of the electrons coming out. Right? You can measure as they leave, you can measure, and it'll be a spread of energies that are shown in this diagram down here. Right? Those energies are assigned to the electrons. And in this case, we've assigned the original orbital they came from. Right? So the higher the orbital, the less amount of energy it took to kick them out. So this, well, let's see, this is electron, this is, excuse me, atomic orbitals, and these are, so you really can't compare these two. This is for free atoms, and this is for molecules. So the short version is, we know the energy that's going in, right? The total energy based upon, right, Planck's constant times frequency. That's the total energy of our photons going in. And then we measure the amount of energy, kinetic energy of the electrons coming out. Right? As they come out, they'll impact a detector, and you can tune it so that you can measure the amount of energy that each electron has striking it. And then the rest of the energy is the what would we call it? Transition or orbital MO energy. That would be better. MO energy. The energy that was required to move the electron from the molecular orbital to infinity or zero energy. It leaves the molecule. So these two together, you know this one going in, measure that one, you can calculate this one. So what's the energy of that molecular orbital? And that's what this gives you. And when we do that and compare it to the calculated values from the mathematical formulas that go into molecular orbitals, we get perfect agreement. And that's the whole reason for this slide, is that the theory agrees with reality. And that's the best you can have. Okay. Any questions? Or are you thoroughly confused? I know that's a lot to digest. And that's about the best I can do of an explanation. So next Tuesday, I think we'll take version 2 and use it as our guide for review. So if you want to spend most of your time, start on number 2 first. And if you get through it, fine. You can go to number 1 if you want.